Okay, this is the Managing Complexity talk. I'm Matt Harrison. And just to start off the talk, I'll give like to warn you, this was listed as intermediate. I'd put it more at a beginner intermediate level. So take heed of that. And I want some audience participation. So raise hands if you're doing testing of your code. Okay, good job. Raise hand if you're measuring line coverage of your code. Okay, good. And raise hands if you're measuring complexity of your code. A few of you, okay. You might be bored, just warning you, if you're already doing some of this stuff, but hopefully you might learn something. So that's my warning. You can leave now and go learn about PyPy or something else. Another warning, this is not about big O notation, so if you think I'm talking about algorithmic complexity, I'm not going to be talking about that. Feel free to leave, you won't bother me. And another warning, this is not, I don't claim that this is a silver bullet that's going to solve all of your development woes per se. Hopefully it's something that you can put in your tool belt and use during many stages of the development pipeline. So the impetus for this talk sort of arose from work in a previous company. We were involved in the management of complex open source stacks. So you have 7+ runtimes, and one of the more complex ones had a Apache 2 on front, proxying out to 2 programs on Apache 1.3, running PHP talking to Postgres, proxying out also to a JSP Tomcat that was talking to Postgres, and proxying out to a VMware image, running Windows with an IIS server inside of it and SQL Server. And we were doing integration of open source stacks and testing and certification of those. And so we, in order to do complex stuff like that and sometimes silly stuff, we wanted to have metrics to keep track of what's tested, what's not, know what's going to work, what's not going to work, especially when you're integrating all those different components. So we wanted to have these measurements. And so basically metrics for pointy heads, the idea is that you want to keep metrics because you can only change something that you can measure. If you're not measuring it or tracking it, it's hard to change that. Great, but for developers, is that useful? So for developers, hopefully there's something that you can do with your metric. Hopefully it indicates something useful to you. So we're going to go over a few metrics. Recently there was a blog poster who's pretty prominent who suggested that the mother of all metrics was lines of code. So basically you take your code and you wrote this long article about how lines of code is a good metric. Now, how useful is lines of code as a metric? So I took the SQL Alchemy project and did a lines of code measurement on it. And it has 57,000 lines of code. What does that tell you? Well, there's actually stuff that will say, given this many lines of code, it has X dollar value because it would have taken this long to develop it. So is that useful? Maybe to a manager type it might be useful. But tracking this measurement, how is it useful? Perhaps it'd be more useful if I told you that of SQL Alchemy's 57,000 lines of code, 31,000 lines of it is actually test cases. Does that help? Maybe. You might feel a little bit more comfortable using it. It might not make the manager happy that you're wasting all this time writing test code. So there's a good quote by a good guy who talks about this. And basically he says that this is a silly metric. So whether you love him or hate him, he might have some reason here. Is lines of code an actionable metric? What can you do if you have lines of code? Well, what do you want to do? Do you want to increase lines of code? Do you want to decrease lines of code? After a certain point, you refactor and you compress enough that there's not much you can do. So for some, refactor, compress, rewrite, and profit. That's how you can use lines of code. If you're interested in running lines of code, there's an open source project that will do that. It's called slot count. So you can install that and you run slot count on the directory containing your code, and it will tell you this line of code metric. So we didn't really use lines of code because with 7 language runtime, C, C++, Perl, Python, Java, it didn't really make sense because it's apples to oranges. So let's look at unit tests. What do unit tests measure? If I tell you you have 10 unit tests, what can you do with that information? Are unit tests actionable? Yeah, you can rerun unit tests after you've changed your code and you have a regression sweep. But you really want to combine unit tests with something else in order to give you a measure of its utility. So that's when coverage comes into place. So I saw some people raise their hand. Some people were testing or measuring coverage and some people weren't. So we're going to briefly go over what coverage is. I hope I don't bore you to tears here. Hopefully it's useful. Coverage itself is a vague term, and you need to be careful when you're using it because it can mean different things. There's different types of coverage. At the most basic level, there's statement or line coverage, and then you have branch coverage, and you have path coverage, and you can have functional coverage and intranexus coverage. All these sorts of coverage. So if you're just saying coverage, normally it means statement or line coverage, but it could mean something else. So if you want to, I'm a picture sort of person, and if you want to understand what coverage is doing, for me it helps to look at it as a picture. So if you convert some code to a graph, on this graph on the right, that's sort of a graphical representation of this silly code here. In order to get line coverage, basically what you need to do is you need to execute every line of that code, okay? So if you have a test case that passes in foo and bar is true, the red line there indicates your path through the code, but basically it's going to execute every line. Now for branch coverage, you want to execute every branch. So if there's a true value or false value, you want to execute that. So normally these coverage tools, they're cumulative. So subsequent runs sort of add up, and then you get your total coverage score. And so if you want to execute every branch, you take your first one that you ran that gave you 100% line coverage, but there's also these if statements. So you want to test if the if is true, and you want to test if the if is false. And so to do that, you have to say foo and bar is equal to false. And with these two tests, then you get branch coverage. And then you enter path coverage where if you're trying to do path coverage, you want to test every path through the code. So you take your first two tests, and that's going to give you some of your paths through the code. And then there's these two more where foo and bar are the opposite values of each other. So that's path coverage. And as you can imagine, trying to get path coverage, if your code has any complexity at all, it gets hard really fast. So again, what does coverage indicate? If you have 100% line coverage, what does that mean? What can you do with that? So sort of to give an example of coverage, I'm going to do a bad analogy here of this guy named Wigloff. He was one of Beowulf's compatriots, and when I read Beowulf, we only focused on Grendel, but actually Beowulf, after he fought Grendel and killed Grendel's mom, there was this dragon that was wreaking havoc in the countryside, and Beowulf went to go fight it with his armies, and all of his army retreated except for this guy named Wigloff. And they fought it together, and Beowulf, short story, Beowulf gets killed, Wiglaf survives, but Wiglaf, during the battle, his shield, he brought a shield with him, protecting from the dragon, but his shield was wooden. So the dragon, who breathes fire, burned through his shield. So, that's the bad analogy. So what does coverage indicate? If I'm going to battle, do I want a SWAT, those SWAT team shields that are Kevlar and go from head to toe, or do I want a wooden shield, which only protects a certain part? So I have these uncovered areas. Those are definitely vulnerable, but just because I've covered something, just because I brought a shield, it doesn't necessarily indicate that my shield isn't made of tinfoil or wood or whatever. Coverage, if you're doing line coverage, you could think of that sort of as a wooden shield. So in pictures, you might have something like that for the picture guys. Watch out for burning heads and bring metal shields. There's also been some research done into coverage, and so people who think they're getting good coverage on their code, they say, oh, I'm getting 85% coverage. Really, you're only getting half of that. So the lesson is, if you are interested in coverage, actually measure coverage instead of just guessing it, because you're probably getting less coverage than you want. And there's a couple tools in Python that let you do coverage. One of them is figleaf, the other one is coverage.py. Here's an example of running figleaf. You install it, instead of calling Python on the program you want to run, you run figleaf, and then you get the output and you change it to HTML, and you can look at your output in HTML, and it will put red lines on the stuff that you didn't cover. So what other metrics are there? This was sort of my dilemma, since we were doing all these metrics at work, but were they useful? It was hard to say. So one day I got this email, and I got a code review via email, which was sort of interesting, but since the reviewer was on the other side of the world, it was okay. And he gave me all these things about why my code sucked, and basically it was like, in Java, every class goes in its own file, and you put 3 classes in one file, so that's bad. And I kind of blew all of that off, but he actually had one point in there, and he said, your code is too complex. Your code is 13. It should be less than 10. And I was like, okay, what does that mean? And so it led me to look at this other metric that my colleague mentioned to me. So let's talk about complexity. There's this semi-famous research done in 1956 which said our humans' working memory capacity is 7 plus or minus 2, or around 2.5 bits of information. So that, if I tell you to remember 6 numbers or 6 letters, or you're going to be able to remember between 5 and 9 of them normally. And that's a problem because our brains haven't followed Moore's law. Computers, programs are getting more complex, but our brains are not keeping pace. So maybe we should, I don't know, have Intel make some brain juice or something to help us out. And here's sort of the morning incantation. You can sort of look at yourself in the mirror and say, I'm dumb, I'm stupid, write stupid code, write simple code, because my brain is so small I can't comprehend complex stuff. So here's Dietrich's quote from 30 years ago. And so, long story short, this brings us to this what's called macabre or cyclomatic complexity. And it's a metric that measures the number of conditions in code at a function or method level. How many people in here have heard of this? Okay, a good percentage. Does it have actionable output? So if you get output from a cab, it's going to look something like this, and here's the 13 that my coworker said was too complex. And these are methods or functions in my program, and some of them are 2, one's 4, one's 13. 13's too complex. And here's the explanation. 1 through 10, it's It's a simple function. There's little risk in it. 10 through 20 more complex, 21 through 51 complex, greater than 50 untestable. So when can you use this metric? You can use it during development, sort of to keep yourself on track. You can use it during maintenance. Usually what happens during code maintenance is you're adding stuff to the code, you're increasing the complexity. You probably want to try and limit that. It's very useful during test planning, and you can also use it to help you in refactoring or rewriting making decisions to rewrite versus refactor. So some more bad analogies. If I'm sitting next to you in the conference and you have bad BO or something, it might be silly. You might think it's an opinion that I say you have bad BO. But if I had the BO meter, which is like some sort of Geiger counter that says, oh yeah, you do have bad BO, maybe it might be offensive, but you could say, yeah, it's sort of a fact rather than an opinion. Likewise, the useful thing about like a McCab complexity metric like this is that you can, like my coworker did to me, you can kind of shove it in their face, and it's not necessarily coming from you, like, oh, your code doesn't look like Java, but your code is complex. You should probably do something to change that. Let's look at how you calculate McCab complexity really quickly, and it's actually related. You'll see why I talked about code coverage previously here. So if I have this code, and this is a pretty simple but dumb code, but it illustrates its point. I have a function that's supposed to leave the value of b as it found it. So the first thing you want to do is you want to convert it to this flow graph, and so you have an entry point and an exit point, and then you go through and you find all of your conditional statements. And you know, there's a branch there, so I'm going to put that in. Here's another branch, and I'll put that in. And now I have my flow graph for my code. Now to calculate complexity, once you have this flow graph, it's this formula at the bottom. V of your graph is equal to the number of edges minus the number of nodes plus 2. So 9 edges minus 8 nodes plus 2 is 3. This code has a cyclomatic complexity rating, or McCab complexity rating, of 3. There's an easier way to calculate this. If you have a planar graph like this, you can count the number of regions. So there's an outside region, there's a region inside that green chunk, and there's a region inside the red chunk. And so that's another way to calculate complexity. And the easiest way is to you can count the number of conditions, binary conditions, and add 1 to it. If you've got like a switch statement in other languages, then you count the number of branches that come out from that. And I should note that complexity is not necessarily the same as length. You can have long code that's very simple. You can have short code that's complex. And so if you're taking if length is one of your metrics, note that they're not necessarily related here. So how does complexity relate to testing and coverage that some of you guys are doing in here? How does knowing this metric relate to that? And one of the things it's useful for is it indicates the upper bounds of the number of tests you need to do to have branch coverage. It also indicates the number of basis paths for this thing that's called structured testing. Has anyone in here heard of structured testing before? A few? Okay. So what are basis paths? Basis paths are the set of paths through your code that can be linearly combined to create any path through your code. And structured testing is basically testing those basis paths. If you execute those basis paths, the idea being that it's sort of simulating full path coverage, because the linear combination of those basis paths combining them, you can do any path. And it also it gives you another metric that's useful in that if you actually have the basis paths, you're sort of done doing your structured testing. Whereas, some testing, it's hard to tell whether you're done or not. So here's a graphical illustration of that. Along the line sort of represents this continuum of different types of testing and the number of tests required to achieve these different types of coverage. So, you have no coverage on this one side, and then you have line coverage, and branch coverage is a superset of that. And branch coverage, the upper limit, in order to have branch coverage, you run the number of tests that's about equal to the complexity rating. And that's how many tests are going to be the upper bound for branch coverage. And structured coverage is just on the other side of that number. Yeah?
How do you know you're running the correct tests just by their number? I mean, I can put together 10 stupid tests, and all of a sudden I think I have branch coverage because my complexity number is 5. Yeah. How would I know that I'm correct?
Yeah. So the question Greg asked is, how do I know I'm running the correct tests? And I hope I'll get to that in a moment. If I don't, raise your hand and harass me about that. So, bad news, Greg. Branch and path coverage is currently not available to Python. Yeah. And there's also no tools that calculate the basis paths programmatically for Python either. So right now it's sort of a manual process. The good news is that this project just came out called Python for Apply. Has anyone in here heard of that? Basically, it allows you to transform Python code into other Python code. And so that could actually help deal with the branch and path coverage issue because you can get around the limitations of the system tracing that don't allow coverage to work right now. So there's been some talk on the testing mailing list about using a tool like this to actually implement branch and path coverage. So, if you're actually managing complexity, then what do you do with it? You can use it to refactor. You can use it to do in your code review to tell someone their code is too complex. If you don't like looking at it, you can use it as an indication to rewrite code. And if you want to calculate complexity, there's this tool called PyMetrics, and it will do it for you. So you extract this tarball. It's not in PyPy, but then you just run PyMetrics on your program, and it will tell you how complex it is. There's a caveat about PyMetrics. So which of these two is more complex, the first one or the second one? What's that? Neither? Okay, good. This man's paying attention. So according to cyclomatic complexity, they're equally complex. The flow graph for the one with the else looks like on the left, and the other one looks on the right. And if you count the number of regions, they're both 2. PyMetrics actually doesn't calculate that quite right. It counts else's as adding to complexity. So if you run PyMetrics, you're going to actually get a number that's a little bit higher than your actual McCab complexity. And I wrote the author of the program about that, but I haven't heard a response. So just take that into account. So, and then here's an example. Again, since there's no programmatic way to do that, and ideally you want that. Hopefully, people who are interested in that, I'm interested in that, and I'm going to look into this code, the apply stuff that came out, to see how to implement that. Here's a manual example of doing structured testing. So McCab also has this, what you call the baseline method. So the baseline method is guaranteed to find your basis paths through code. So basically, the algorithm goes like this. You execute a normal path through your code, and then you execute a path again, and the first condition statement you get to, instead of you take the opposite path, you branch on it, and then as soon as you get back to your normal path, stay on your normal path. And then you go on your first path again, and you skip that first branch because you've already executed the other branch. You come down to wherever your second branch is, and you take that, and then you come back, and you repeat this until you get to your until you've done complexity count pass, and that should give you your baseline pass. So again, it's a manual process right now. Hopefully we can create some code to automate this and tell you if you're getting your basis pass or not. So, and here's a graphical example of the code here. So, I should have mentioned, this code has a bug. Okay? So, if you're using complexity and baseline pass, you're guaranteed to find this bug. If you're doing line coverage or branch coverage alone, you're not guaranteed to find the bug. So basically, here's the example. Your baseline path is both of them being true. That's the blue line on the left. The next one after that, you come to the first statement and you switch it, and you get back onto the same line, and then you follow that branch again. And then you go back to your baseline path, and you take the first one because you've already exhausted all the conditions there, and then you come to the second path and you don't take it because you previously did take it. And you've done 3 tests, the complexity is 3, you're done, and your test cases will indicate, actually the second one will indicate where that you have a bug. Again, the first test there is going to give you line coverage. It's not going to find the bug. And if your second test just looks like the straight line down, that will give you branch coverage, but it won't find the bug either. So, and here's sort of the linear combination note. Note that we didn't do this test here that's sort of the trivial one for branch coverage, but it's actually a combination of these other tests. So there's been numerous studies with complexity, and basically they say that the more complex your code is, and if your code is over 10, which is sort of at this threshold of 7 plus 2, you're more likely to have bugs in your code. And there's also been projects that have used complexity tools that have successfully used them to reduce their count of bugs. There's also, so is code, and previously I said is code coverage actionable? And yes, it is in some case, because you can, if you're trying to cover code and you're just using like line coverage or whatever, you can find dead code because you can try and execute it and you're like, why isn't this code executing? It might just be dead code that you can't execute because you have a logic flaw or something else. And there's also been studies that have shown that if you have dead or redundant code, you probably have a bug in your code. So if you, lack of coverage, like the shield, if you can't get coverage, look at your code. You probably have a bug in it, and studies have sort of confirmed that. There's other metrics as well. One's called this Halstead metric, which takes into account operators and operands and how much space you've written and your code size. And actually, this PyMetrics tool will calculate that as well. The problem I have with it was I get these weird numbers like, remember generic query, that was like my 13. Here it's 1.5 times 10 to the first power, and it's the same as this other one that I think had like a 3 or 4 complexity. And so I'm not sure that I can use that. I haven't, it just looks like a big report that I don't understand what all these numbers mean. So personally, I've run it on some stuff and I just can't grok the information because stuff that appears to me to be more complex or whatever, they're just numbers, and you have something that's very simple and it rates as the same complexity as something that's not simple. So maybe it's a bug in the calculation in PyMetrics, or maybe it's my dumb programmer mind that can't comprehend it. So in conclusion, suggestions, metrics are good. Metrics are better if you can actually do something with your metric and you can take actionable steps on them. So again, you start out with the basics, unit tests. Once you move on from that, try and get some coverage. If you find dead spots or bad spots, remove them, fix them. Code reviews are good. The studies have also shown that the earlier you can fix a bug or find a bug, the cheaper it is. And so do code reviews as well, in addition to testing. And during that time, that's a great time to bring up complexity. Look at how complex your code is. Also, refactor, rewrite, get rid of bad, dead, or complex code, and then do your retesting. And then this last one, my last suggestion, which is being cut off here, is write branch or path coverage code and for Python. So that's a suggestion. If people are interested in that, come talk to me and let's see if we can do something. Anyway, that's my talk, and thanks to all these tools and people who have helped me do it. I hope that together, or people who are interested in this, we can create a tool that will do this, and people who aren't interested in it can take advantage, or who aren't interested in helping can at least take advantage of the tools that are out there and make their code better. And so that's my talk. Any questions? We got time for a couple questions, yeah? Okay, so I think the question was, if you refactor and you pull out code, you're pushing down the complexity, you're lowering the complexity, how does that help you? Is that your question? Yeah. Basically what that allows you to do is to test the refactored code better. And so you have smaller things to test. Once you get something that has all these different paths or branches through it, you get a combinatoric explosion of different ways that you have to test it. If you have a smaller, simpler code, it's easier to test and find the path through it.
What are the challenges preventing the
The question is, what are the challenges for implementing cyclomatic complexity in Python? Implementing something so it's already implemented, right? PyMetrics would tell you what cyclomatic complexity is, but it's a little off. There's a one-line patch to make it so it's not off. To actually measure paths and do basis paths, then you've got to go through the tree of your code. You've got to parse the code and use the AST library and create a tree and create graphs, and then you need to actually have coverage reports. And the problem with coverage is that current coverage the granularity of coverage is at a line level right now. So if you have a short-circuited conditional statement like if, foo, or bar, you don't ever know if the or is getting executed or not, because it's only the line level granularity. So that's why you need to use something like apply to actually translate all those ors and ands and stuff that can get short-circuited into individual line numbers that map back to the original. So, just a simple matter of programming. Yeah.
Actually, my question is related to your comment here. So, if else is like an explicit branch, but you have also implicit kind of flow control, like you can use a dictionary instead of a string. So, is there a way to take this into account?
The question is, how do you, since Python doesn't have a switch, but you can sort of fake it using a dictionary, how do you do flow control based on that? And yeah, sort of the dynamic nature of that makes things a little bit more complex. I'm not quite sure what the best way to handle that is currently.
I would think the best answer would be take the dictionary out. It's refactoring code, so you're not using the dictionary. I mean, that may not be possible in all use cases, but that to me would seem like the best way to reduce the complexity there is to actually explicitly take out that dynamic nature so you can manage.
Okay, That's time, but the answer was, you know, if you're using a dictionary, maybe you want to pull that out. The suggestion is pull out the dictionary. Again, if you're doing dynamic, you know, fancy stuff, that might not actually work with your code. So that's one solution. Okay, thanks everyone.